Okay, so we'll go back to another video. So here we would like to show that the following limit is equal to the Riemann zeta of 2, aka Bassel's problem, aka pi squared divided by 6. The limit being the limit as n approaches infinity of pi times the square root of n divided by sine of pi divided by the square root of n, and then subtract n. So this is actually pretty interesting that at least now that the Riemann zeta of 2 Bassel's problem actually has some form of a limit representation. So to evaluate this limit, in order to show the left-hand side is equal to the right-hand side, we basically just use a bunch of, algebra techniques. And the interesting thing is rather that what is going to throw people off when you first see this at first glance is that sine, the sine function over here. So we can actually utilize this in a different property that we can actually make things a little bit simpler actually by using the Taylor series. So that actually gives that one thing away from one of the steps on what we'll be performing, but it actually just comes straight forward from there. Everything's using just algebra from straight on. So pretty simple to some extent. That out of that I just gave that to you, and also a cool evaluation to show that indeed that this is equal to this Riemann zeta 2. So let's actually get right into it and show that. So the first thing we'll do is let's actually factor out the n of our limit. So let me just write this in parentheses first. So the limit as n approaches infinity, so n, and then multiply. So we have a square root of n at the top. If I factor that n out, so in other words, that's actually written as the same thing as pi divided by the square root of n, and then still being divided by sine of pi divided by the square root of n, and then just subtract 1 over here. Okay, so we're actually going to do a little bit of a substitution. Suppose that if we let t, we'll let that equal pi and then divide it by the square root of n. So also keep in mind that we have to put in something for n on its own. So let's actually solve for n on its own. Pretty simple to say that this is just n is equal to pi squared divided by t squared. And another thing to note that if we were actually changing this into a different variable, notice that as n approaches infinity for over here, so as n approaches infinity, so then that would have to imply that t will have to approach 0. So with this, we can actually now write this in a new limit written as follows. Now this time we have the limit as t approaches 0 of now pi squared and then divided by t squared. So that's just factoring out or substituting n for this substitution over here. Then now everything we have is t from here, then divided by sine of t and then subtract 1. Now, as mentioned, the sine of t is actually a little bit complex, such that it actually looks a little scary on how we're dealing this to show for the Riemann zeta. But as mentioned, we will actually be utilizing the Taylor series property of that expansion. So now what we have is that the Taylor series expansion, so let me first write this out again, that limit as t approaches 0, pi squared divided by t squared. Then on the denominator, what we have is, so first is t, and then the Taylor series expansion of t, then subtract t cubed divided by 3 factorial. Add this with t to the power 5 divided by 5 factorial, then subtract t to the 7 divided by 7 factorial. So the expansion goes on, so forth. We don't need to worry about more to that. So then subtract 1. Okay, so now let's actually distribute the t squared from the denominator, everything back into over here, and also distribute it to the -1 as well. So applying that, so we have now, this is going to be the limit as t approaches 0 of pi squared. And then now this is multiplied by, so everything on the denominator we have is going to be t squared, then subtract t to the power 4 divided by 3 factorial. Add this with t to the power 6 divided by 6 factorial. Subtract t to the power 8 divided by 7 factorial. This is actually meant to be a 5 factorial, my mistake over here. And then we continue on that expansion, so on and so forth. So that's actually going to be a 1 on the top. And that's also because that we have a t, so that means that also cancels out one of the t. Then we distribute the t into everything over here. Then now we have finally subtract 1 divided by t squared. Okay, so with that out of the way, so how do we actually perform something like this? Well, this is actually interesting because we're actually going to do a little bit of some long division to simplify this expression a little bit further. So let me now put this with our dividend and our divisor over here. So to perform that long division, so I have t squared, then minus t to the power 4 divided by 3 factorial. Add this t to the power 6 divided by 5 factorial. Then minus t to the power 8 divided by 7 factorial. Then so on and so forth. So this is divided by 1. So or 1 divided by this divisor over here. So now all we have to do is long division, just choose whatever it is to put down for here. We multiplied that and then we do the subtraction. So first we can actually now multiply the 1 divided by t squared. So by doing so, that means that's going to give us with, so we have to subtract the terms. I'm going to put a minus and then in parentheses what we're subtracting from. So we have 1, then minus t squared divided by 3 factorial. Add this with t to the power 4 divided by 5 factorial minus t to the power 6 divided by 7 factorial, and then so on and so forth. So continue on with that expansion. So if I just subtract the term, so that means the 1 disappears, and now we're just left with t squared then divided by 3 factorial minus t to the power 4 divided by 5 factorial. Then add this with t to the power 6 divided by 7 factorial, and so on and so forth. So now continue forward, we just do the same thing. So now let's actually now multiply. So plus 1 divided by 3 factorial. So by doing so, we have that, we multiply everything in over here. So subtract with the quantity. So I have t squared divided by 3 factorial, then subtract t to the power 4 divided by, so I'll write this as 3 factorial quantity square. Then add this with t to the power 6 and then divided by 3 factorial times 5 factorial. We just continue the expansion. So rather, this is actually supposed to be a minus, but you know, that's okay because, so over here. Okay, so now if I just now subtract the terms, everything, so that means that's going to cancel. So over here that I have a 5 factorial, 3 factorial square, so 36, and then times what 5 factorial is 120. So you put that out, you get a denominator of 4,320. So you do the cross multiplication to get the numerator, that will be 84. 84 divided by 4,320 is the same thing written as 7 divided by 360. So 7 divided by 360 multiplied with t to the power 4. I'm not going to sweat all the details about writing the rest of the expansion, so I'm just going to follow it with the more ellipse. Then let's actually continue one more such that now we can actually now multiply. So now plus 7 divided by 360, then multiply with t to the power square, so t squared. Now I'm just going to follow with the ellipse over here because we're not really going to sweat the small stuff in here. So minus, so that means 7, 360, then t to the power 4, dot, 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 so on and so forth. That's, again, this is an infinite expansion. We don't have to worry too much about that because what's nice is that if we put all this back together, this is our new, like, multiplier from there. So substituting that, I have the limit as t approaches 0. So substitute everything for here back into the denominator over here. And now we have a minus 1 over t squared. Don't forget that. So now this is going to be, so what is it, pi squared? Pi squared, and then divided by, so 1 divided by t squared, then add this with 1 divided by 3 factorial, add this with 7 divided by 360 times t to the power 4 plus dot, 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 so on and so forth. Then now that's supposed to be subtract from the 1 divided by t squared, and that's great since that these two are just going to cancel each other out. And then what's left is that now we have, this is the limit t approaches 0 of pi squared, then divided by 1 divided by 3 factorial plus 7, 360, then t to the power 4. Again, not sweating the small stuff because this is nice that everything from here on out and so forth is actually just an expansion of polynomials. So meaning that if I were to take that as it approaches 0, everything from the end except for 1 divided by 3 factorial is going to disappear. And so therefore we're just left with pi squared then times 1 divided by 3 factorial, which is of course 1 divided by 6, aka pi squared divided by 6, Basel's problem, actually the same thing written as Riemann zeta of 2. And that is indeed validates that this is indeed our final answer for that limit that we were given to, you know, perform that validation, just like that. So there you have it. So yeah, that's pretty cool if you ask me.